We're happy to have, we've already introduced Professor Kharzeev, so I'll just ask him to go ahead and give us.
Okay, wonderful. Hello, everyone.
I'll give you a warning at the end of 50 minutes.
Yes, okay. So thank you very much. Today we will have the final lecture on the physics of chirality. And in the previous lecture, we discussed the chiral magnetic effect, considering magnetic field and the chiral chemical potential as fixed backgrounds. But of course, this is a big simplification. So we already know that the chiral chemical potential is not even a conserved quantity. And we also know that the chiral magnetic current will back react on magnetic field. And this back reaction has to be taken into account. And so today we are going to discuss a dynamical setup in which neither the chiral chemical potential nor magnetic field are considered as fixed. So for example, if you have a closed ring of magnetic flux, and you have a chiral chemical potential, there would be a current flowing along magnetic field. This current will back react on a magnetic field according to Maxwell equation. And as a result, the lines of magnetic flux will start getting twisted. So if you plug in current in this expression, you find the following equation. And this is an equation which was studied by Chandrasekhar and Kendall. And its solutions represent knotted configurations of magnetic flux. So because of this, chirality can be transferred from fermions to chirality of magnetic flux, which is noted in chiral knots. And you can see that the source for anomaly, E dot B, can be represented as the time derivative of magnetic helicity, which we have introduced earlier. So the chiral anomaly indeed sources the change in time of magnetic helicity, which means that there have to be reconnections of magnetic flux. So anomaly will cause the chirality of these knots to increase. And in closed system, the total chirality of magnetic flux and of fermions is conserved, but you can transfer chirality back and forth between fermions to magnetic helicity or vice versa. So there is a very interesting phenomenon of chiral magnetic instability, which takes place here. And it was actually noticed in physics of plasma even before the discovery of chiral anomaly under the name of so-called alpha dynamo. And the physics is the following. So suppose you have a magnetic field pointing in this direction. And suppose we get the current, which in our case is the chiral magnetic current. In the old days, it was just a fluctuation of current, which happened to happen along the direction of magnetic field. Then this current will generate magnetic field around it, according to Maxwell equations. Now, along these new lines of magnetic field, there will be a new chiral magnetic current. This chiral magnetic current will in turn back react on a magnetic field. And so you can see that you set off a cascade where you really transfer helicity of stored in the current into helicity stored in this knotted magnetic flux. So now This instability happens at small momenta below anomaly coefficient times the chiral chemical potential. It leads to the growth of magnetic helicity. Once magnetic helicity increases, since the total helicity in the system is fixed, the helicity stored in fermions goes down. This in turn shifts the instability to smaller momenta. And so you get this inverse cascade of magnetic helicity. So this chiral nodes of magnetic flux start growing in space. And so this is phenomenon which was studied in these papers. And what has been noticed relatively recently by Yuji, Yin, myself, and Naoki is that this self-similar cascade of magnetic helicity, that this cascade of magnetic helicity is actually self-similar with exponents of diffusion. So we really have kind of diffusive growth. And this self-similar inverse cascade now finds interesting applications in description of helical magnetogenesis in the universe. And there may be a link between this helical magnetogenesis and barrier genesis. So this is what happens when you include back reaction of chiral magnetic effect on magnetic field. We can go one step further and abandon the description of chirality imbalance in terms of chiral chemical potential, because we know that the chiral chemical potential originates from geometry of gauge fields. And so we can just consider the chiral magnetic current, which emerges when the topology of gauge field gets changed. And we will see that in this case, we can express the chiral magnetic current only in terms of the change of topological invariance of chiral nodes. So for example, suppose I have this right-handed trefoil, which as a result of magnetic reconnection goes to this ring of magnetic flux or unknot. Because this is accompanied by the change of magnetic helicity, this time derivative does not vanish, and this time derivative is exactly the source of anomaly, so it is accompanied by electric field. So now, the change of magnetic flux through the interior of this ring gives us electric field, and electric field will generate, of course, electric current of fermions. So this is the density of the current, and L is the length of this flux, and Q is the charge. So now helicity change per magnetic reconnection is 2 phi squared. And if you have, let's say, n plus positive and n minus negative crossings on a planar knot diagram, here is the total change of magnetic helicity. And you can prove by induction that the total current induced by reconnections to a chiral knot is just given by this change of magnetic helicity. So again, I can multiply both sides by L, and then I will get the total current instead of current density, and it will be expressed only in terms of this chiral invariant and electric charge. So this means that chiral magnetic effect really is a purely topological phenomenon. And as I mentioned before, people at present study this inverse turbulent cascade of magnetic helicity in the early universe with very interesting implications for cosmology and astrophysics. So now this brings into consideration the question of what happens when magnetic fields are time dependent. So we addressed chiral magnetic effect in time dependent magnetic fields with Harman some time ago using perturbation theory, linear response, and the one loop computation. And we found that at non-zero frequency, the chiral magnetic conductivity abruptly drops to a value which is 1/3 of the value at zero frequency. For quite some time, there was a puzzle in understanding this 1/3, because if you described this chiral magnetic effect in terms of chiral kinetic theory, then you would find the contribution from Berry phase, which would give you 2/3 and not 1/3. And this puzzle was solved in this paper with Wong and Misha, where we found that one also has to include magnetization current, which contributes exactly minus 1/3, and this gives 1/3 overall. Now, at zero frequency, the magnitude of the current is completely fixed by topology. However, at finite frequency, this is not so. For instance, Hong and others computed the frequency dependence of chiral magnetic conductivity using holography at strong coupling. And we see that even though the values at zero frequency coincide, at finite frequency, the shape of the frequency dependence is quite different, which of course should not surprise us. So an interesting lesson from this holographic studies was that the chiral magnetic effect persists at strong coupling. And we know that at strong coupling, we have a universal low energy effective theory, which is hydrodynamics. And so this posed the question of whether CME can be included in a hydrodynamical formulation. So at first glance, it looks like chiral anomaly and hydrodynamics are, completely different phenomena, from different volumes of Landau-Lifshitz course. However, if you think a little more, you realize that hydrodynamics is an effective low energy theory, which is entirely based on conservation laws. Conservation laws are a consequence of symmetries of the underlying theory. And so when some of these symmetries are broken by quantum effects, anomalies, the hydrodynamics should probably notice. And Son and Sorovkar were the first to introduce hydrodynamical description of this phenomena, assuming that the local entropy production rate has to be larger or equal to 0. So this is the standard hydrodynamical assumption. And they found that they can constrain first order hydrodynamics by this condition. So what we did with Hong, we observed that the true constraint is actually tighter than the usual positivity constraint for local entropy production, because if you apply parity transformation, then the anomalous contributions to the entropy production rate are parity odd. And this means that if you look at your fluid in the mirror, then this parity odd coefficients should change sign. And if you had some positive entropy production rate, in the mirror, you would have to have a negative entropy production rate, which should be ruled out by second law of thermodynamics, because you never know whether you are in the mirror or not. And so we proposed that the true constraint should be more tight, that the entropy production rate has to be equal to 0. You can also argue this on the basis of time reversal invariance as well. So this is a quite tight constraint. At first order, you get the same results as Son and Sorovka did. But at second order, you can actually find 13 out of 18 anomalous transport coefficients. So here are the terms that correspond to all of these 18 transport coefficients. And by now, all of these relations have been explicitly confirmed in holographic computations. So this is, I think, really the true physical principle. Okay, so now another thing which happens when you start treating chiral chemical potential as a dynamical variable is that you realize that the chiral anomaly not only gives you this relation, but also the relation of axial charge flowing when you have a vector chemical potential. And because vector chemical potential is proportional to the temporal component of vector current, and axial chemical potential is temporal component of axial current, this means that these two relations actually are coupled. And if you write down conservation for this current, then you find that it immediately gives you an equation for a propagating chiral wave, which has to be a gapless collective mode, which is the carrier of CME current in magnetohydrodynamics. So we computed the velocity of this excitation using holography as a function of magnetic field, and found that in a strong magnetic field, this velocity goes to velocity of light. So this can be understood because in strong magnetic field, everything is frozen on the lowest Landau level. And then it's just the velocity of fundamental fermions, which determines this velocity of chiral magnetic wave. So two of our organizers, and Nicholas and my former student, Mark Mays, did this amazing computation of chiral magnetic wave in real-time lattice. So you can see how the Schlichting transition induces you an axial charge. This axial charge induces a vector current. The vector current, in turn, induces separation of electric charge. And so you really see how these things evolve in real time. And you observe this coupling between axial and vector charges. So this is really beautiful work by Soeren, Sayantan, Nicholas, and Mark. So there is also a very interesting analogous phenomenon induced by vorticity, which we studied with Gökçe and Hon. And here, instead of magnetic field, you have vorticity. And because the current induced by vorticity is quadratic in the chemical potential, when you repeat the derivation for the chiral magnetic wave, you find a different wave equation, which looks like this. And if you look at it for a while and open your favorite mathematical physics textbook, you find that this is the famous Burger's equation. which is exactly soluble, describes integrable dynamics, and has some very interesting solutions like shock waves, solitons, and so on. And I'm quite sure that there are some very interesting phenomena that can still be found here. Okay, but now let me go to the very important question of how to search for all of this in experiment. Whether we can really observe this phenomena in coagulon plasma created in heavy ion collisions. So how would you go about it? Well, you collide heavy ions. The heavy ions produce a fireball of coagulon plasma. These ions also create a strong magnetic field. And then if in this plasma you have a diffusion of Chern-Simons number, then in a given event, you would have some chiral imbalance in a magnetic field. And so this chiral imbalance in a magnetic field will give you a chiral magnetic current, which will create charge asymmetry relative to the reaction plane. So your coagulon plasma will develop electric dipole moment. And of course, orientation of this electric dipole moment will fluctuate event by event. So the creation of magnetic field is a completely classical phenomenon. These are positive ions, so they are surrounded, by magnetic fields, and so you can just use Maxwell equations and compute the resulting magnetic field. And of course, it is a huge magnetic field, which is a couple orders of magnitude stronger than you can find in a magnetar. So I think this is the strongest magnetic field ever achieved in the laboratory, or possibly the strongest magnetic field that exists in present-day universe. So one can also study the evolution of this magnetic field in ideal magnetohydrodynamics. You see that MHD phenomena actually make this field live quite longer due to Faraday induction. So you can also study the coupled to it evolution of chiral charge and electric charge. So in this recent work, this was done in fully dynamical MHD treatment. And so you see that indeed these dipoles of electric charge do emerge in the evolution of the plasma. And so we have to find some way to detect this dipole moment. Okay, so the variable for this was originally proposed by Sergei Voloshin. So this is so-called gamma correlator, and by now there are many variations on these variables. But the main idea is that this is the variable which is sensitive to the separation of charges relative to the reaction plane. So for example, if you take alpha as a positive charge and beta as negative charge, then relative to the reaction plane, one, let's say, goes up, another goes down. So these signs have opposite signs. And this means this bracket is negative. There is a minus in front, so it has to be positive. And so you expect that opposite charges would have a positive gamma correlator, and same charges for the same reason will have the negative correlator. And this is what Starr indeed observed. But of course, it was realized already by Sergei and in this paper that this quantity is really a p-even quantity because it measures the strength of parity odd fluctuations. And so it is subject to potentially large background contributions. So here is the compilation of star and Alice data on this gamma correlator as a function of energy that we did with Jing Feng recently for this review article. And you can see that, you know, there may be some hint of non-zero signal, but the significance is not large. So if you really want to indulge in some visual thinking, maybe there is a stronger signal at lower energies, and I will come to the speculation about the possible origin of this. Star also came up with this very nice idea of testing CME and separating it from backgrounds using Isobar collisions. So what are the isobars? So you use ruthenium and zirconium collisions. So they have mass number of 96, which is the same, and different numbers of protons. So the idea is that because the mass number is the same, the radii are approximately the same, so backgrounds should be approximately the same. But because ruthenium has a higher electric charge, it would create a stronger magnetic field. And so the signal would be stronger in ruthenium. And if everything is background and magnetic field is irrelevant, then ruthenium to zirconium ratios for this gamma correlators and the like will be equal to 1. So this run was completed in May of 2018. 2 billion events were recorded per each pair, and a full blind analysis was performed. And the results have just been released last week. So this is the paper that was submitted by STAR on arXiv. This is the plot which was shown in the paper in their press release. And if you find the abstract of the paper, they say the following, that no CME signature that satisfies the predefined criteria has been observed in isobar collisions in this blind analysis. So if you look here, here is the ratio of this gamma correlators over V2, which is elliptic flow coefficient, between ruthenium, and zirconium. So unity here would correspond to pure background, larger than 1 would correspond to CME. But what they have observed is that all of these gamma ratios are actually below 1. So so this is the basis for this no CME signature. But of course, this ratios being less than 1 is actually quite puzzling, because even if you forget about CME altogether, this ratio less than 1 is not predicted by any theory, be it based on CME or not. Okay, so we have to figure out what's going on. And the point is the following. So as I said, ruthenium and zirconium have the same mass number and therefore approximately the same size. But the key word here is approximately, because it appears that when STAR actually measured the ratio of multiplicities in the centrality cut that was used in this analysis, then the multiplicities differed by about 4%. So, the effect we are looking for is also a few percent. So this 4% is actually a very important correction. And in particular, it has been known for some time that this delta gamma over V2 ratio is scales as 1 over multiplicity. And this is what's written in the STAR paper as well. So they say it may be considered that the proper baseline for the ratio of delta gamma over V2, which is shown here, is the ratio of inverse multiplicities. So I have to say that all of the models that were developed for these observables indeed show that they scale as inverse multiplicities. So this statement is correct. Then they say that analysis with respect to this baseline is not documented in the pre-blinding procedures of this blind analysis, so is not reported as part of the blind analysis. So basically, this rescaling was not done in the presented data. However, they did the right thing and included this inverse multiplicity ratio as the rightmost point in figure 27. So this is figure 27, and this is the ratio of inverse multiplicities. So now, of course, the right thing to figure out the physics conclusion would be to take the appropriate baseline, which is this. And then the baseline, instead of 1, sits at this ratio of inverse multiplicities. And now you see that ruthenium over zirconium is actually slightly above this baseline, which we, of course, expect. And depending on the observable which is used, the CME signal is present at the level which varies between 1 sigma and 4 sigma. So this means that detailed post-blinding analysis is desperately needed. It is currently ongoing. All of the groups involved in this blind analysis are participating in it. And quite soon, hopefully in a few months, we will know the true physics conclusion from this really nice high statistics and precise data. So stay tuned on the Isobar analysis. So now I mentioned that there might be a hint that the signal may be enhanced at lower energies, and what could be the underlying reason. So this was the motivation for our recent work with Yuta and Kazuki. And the question that we addressed is what happens to topological fluctuations near the critical point? Could there be enhancement of Chern-Simons fluctuations due to the criticality? And this is a real-time problem which we addressed using quantum simulations. And since currently technology only allows you to do 1+1 in these quantum simulations, we found a system in 1+1 which has a similar critical point, which is a massive Schlichting model at theta equals 2 pi, which has this critical point at fermion mass over coupling of about 0.33. So the existence of this critical point was pointed out by Coleman a long time ago. So here I illustrate why this happens using the effective potential of this theory. And when we computed real-time topological susceptibility, we indeed found that these Chern-Simons fluctuations exhibit a sharp peak near this critical point. So since this critical point is similar, to the critical point that happens in QCD, this suggests that it might be interesting to search for CME also in low energy heavy ion collisions during the beam energy scan. So I already mentioned the physics of real-time dynamics of CME. So we also addressed this problem together with Utah using this Hamiltonian field theory and quantum simulations. And we found some interesting results. Another interesting topic that we recently addressed related to real-time dynamics of CME is this paper with Adrian Florian, where we considered production of E plus E minus pairs by a pulse of electric field. And of course, this pulse produces a number of E plus E minus pairs, and these pairs are entangled. So let's say this positron is entangled with this electron because they were produced together from the vacuum. So now what we observed is that if you compute this entanglement entropy between left and right movers, then this entanglement entropy appears to be exactly equal to the Gibbs entropy of the produced system of E plus E minus computed according to the rules of statistical physics. So this suggests some interesting connection between statistical mechanics and quantum mechanics. So we also expressed this entanglement entropy in terms of the moments of multiplicity distribution. So we discovered that this formula was first derived by Clich and Levitov for describing shot noise in quantum point contacts. So this is important work for decoherence of superconducting qubits. So there is some interesting connection here. And we found an efficient way to resum this series from, turning it from asymptotic to some much better convergent series. And we also found that short pulses actually produce an entropy which is approximately thermal, with the temperature which is 1/2 pi times duration of the pulse. Okay, so there is clearly a lot to be understood here, and sort of reformulation of all of this in terms of entanglement entropy, I think is an interesting topic that we will continue studying in the future. So in the remaining 12 minutes, let me mention some other applications of this physics in condensed matter and quantum information. So these chiral quasi-particles exist also in so-called Dirac and Weil semi-metals that recently attract a lot of attention. So you can see this linearly dispersing chiral quasi-particles. And of course, we already had graphene, but these are three-dimensional crystals. This means that chiral anomaly operates. One can study CME. And this is what we did in zirconium pentatelluride. And we subjected it to parallel electric and magnetic fields. And these parallel electric and magnetic fields sourced anomaly in the chiral chemical potential. And in a magnetic field, you get the chiral magnetic current, which manifests itself through the characteristic quadratic dependence on magnetic field. So if you add this one to the conventional ohmic one, you find the negative magnetic resistance, and this is the theory and the experimental data. So by now, this is firmly established in several dozens of different materials. Some of these materials exhibit this at very high temperatures, and effect is really extremely strong. You can enhance, this conductivity by a factor of 100. And now the emphasis of these studies is shifting to optics. And one question is whether one can control CME by circularly polarized light. So in the first lecture, we already discussed that circularly polarized light is characterized by Chern-Simons invariant. And when it is absorbed in this material, it creates the chiral chemical potential. So if you put a crystal in a magnetic field and shine on it a circularly polarized light, you expect to find substantial current. So this can be done in either Weil or Dirac semi-metals. So these currents indeed exist. And moreover, as was found in this recent paper, in which my students and I collaborated as theorists, not only these currents appear, but these currents also back react on electromagnetic field, and you can measure this near field, which also has a circular polarization depending on the chirality of the current which is induced. So note that this was done at room temperature. So another interesting idea is to, instead of light or electric field, to use strain. And this is the work by Lan Gao and my students Sahal and Evan. So now, how could we use all of this? Well, we know that currently everyone is interested in quantum computing, and among the leading technologies is superconducting qubit technologies, where the corresponding processor operates on the Josephson tunneling between different superconducting islands. So now the question is whether we can organize a similar system using chiral fermions, where the tunneling would be not between superconducting islands, but between left and right-handed fermions mediated by chiral anomaly. So the simplest model toy example that one can think of is a thin ring made of Dirac or Weil semi-metal coupled to a magnetic flux. So you can easily derive this Hamiltonian from this Lagrangian, where phi is this magnetic flux, which can be used for control. And different eigenvalues of sigma z correspond to different chiralities, left or right. So sigma z is gamma 5 in 1+1. So this is the spectrum of this Hamiltonian. Of course, you have this infinite tower of negative energy states. You have to sum over these negative states, as was known for a very, very long time. And once you perform this summation, you recover formulas for CME current in 1+1 dimensions. And you also recover the effective Hamiltonian, which you obtain after summing over all of these negative energy states and regularizing this sum. And here a small miracle happens. because this effective Hamiltonian appears to be identical to the Hamiltonian of the superconducting qubit. So this means that in principle, all of the same gates and so on can be used in this system. You can control these qubits using circularly polarized light, infrared or terahertz. You can use external magnetic flux. Then, because we already know that these currents backreact on magnetic field and create this polarized near field, this polarized near field can be used to entangle qubits. You can place them in so-called split ring resonators that operate at terahertz frequencies. And so, in principle, this might be idea that might be realized. At present, we work on it with a number of collaborators, both theorists and experimentalists. And so, a time will show whether we will succeed in replacing this superconducting qubits by some kind of chiral qubits. So one thing to notice is that superconducting qubits, of course, have much longer coherence time than these qubits, because these times now approach millisecond. And here, the lifetime of this chiral quasi-particles is at best 100 nanosecond. And so this would seem to rule out this chiral qubit devices. However, the figure of merit in quantum computing is not the coherence time per se, but the ratio of coherence time to gate time. In other words, it's how many operations can you perform on a qubit during its coherence time. And if you look at this ratio, then for known materials, you might hope to reach this coherence to gate time of about 10 to the 4th, 10 to the 5th, which is comparable or maybe even better than the best existing superconducting devices. But of course, this idea is still at the infancy stage. So it's I cannot tell whether it will really work at this time. But I think it's an interesting topic to investigate further. So. To summarize, in the remaining 1 minute, I hope I convinced you that chirality is an interesting topic to study, both in classical and in quantum physics. In quantum field theory, it leads to the chiral magnetic effect and related quantum transport phenomena, which are direct probes of topology of gauge fields. So CME in heavy ion collisions is a unique opportunity to observe these topological fluctuations in the laboratory. So this topic is very far from being closed, but I do hope that within a year or two, we will have a definitive answer on this. CME has been already discovered in many chiral materials, with important present and future applications that range from sensors of terahertz radiation to maybe even quantum computers. So this is the end of my time, and I would like to leave time for questions. So thank you very much for your attention.
Thank you, Professor Kharzeev.
And if you are interested in learning more, I will also include in my slides this list of review articles that you can consult if you would like to learn more.
Thank you. We have time for some questions. You can raise your hands or unmute yourself and ask.
So I wanted to ask, hello?
Yes, I can hear you.
Yeah. Okay. So I wanted to ask about the last topic that we touched upon, using chiral qubits to probably replace superconducting qubits in quantum computing.
Mm-hmm.
So do you have any idea whether logistically is it feasible to replace probably in future if you want to use chiral qubits in place of
Okay, so so first of all, let me tell you why I think it's worth trying, right? So first of all, you know that superconducting qubits require milli-Kelvin temperatures to operate, right? Because at higher temperatures, you break the coherence, and you really need to use this big dilution refrigerators to cool this down to milli-Kelvin temperatures. So the biggest expense of operating a quantum computer is really, maintaining this milli-Kelvin temperatures. So the chiral magnetic current already at present has been observed at temperatures up to 150 Kelvin. So, it's a huge, factor in temperature. So, and this optically controlled chiral currents we have seen even at room temperature. So temperature is one big advantage why you would want to move from superconducting qubits to chiral qubits. The second advantage is operating frequency. So the frequency of quantum superconducting quantum processor is determined by the frequency of AC Josephson effect, which microscopically is determined by the magnitude of superconducting gap. So this tells you that the characteristic clock frequency for a quantum processor is in the gigahertz range. So you cannot kind of operate it faster than at gigahertz frequency. It may be 10 gigahertz, but it's in of the order of gigahertz. So now here, because we have a large energy interval where the band in this Dirac and Weil materials remains linear, and in some materials also the gap to first non-Weil bands is quite large. We can hope, and we already can do it experimentally, we can switch these currents at frequencies which are in the terahertz range. So this is, a huge factor. So it's like a factor of 1,000 in clock frequency of the processor. So the two biggest advantages are the high temperature and much higher frequency. So the disadvantage is the low coherence time of this chiral quasi-particles, but as I already explained, what matters is the ratio of coherence time to gate time, and here we are at least, we may hope to be at least as, to be as good as in superconducting qubits. So the biggest problem at the moment, the biggest challenge that we are struggling with is similarly to what happened in the development of superconducting qubits, is to ensure a large coupling of these chiral modes to the electromagnetic modes in the cavity. So in superconducting qubits, some special effort was taken. So people designed some antennas, for coupling to microwave cavities. So here we have to work with infrared or terahertz frequency fields. And so some corresponding technological development enhancing the coupling of currents to electromagnetic modes in this cavity has to take place. But the experts tell me that this might be possible.
Okay.
So did I answer your question? Mm-hmm.
Yes. Thanks for the talk.
Mm-hmm.
There's a question by Norioke. So go ahead.
Hi, I have questions on your slide. You explained the negative magnetic resistance, and maybe you explain some that one. So the message towards the room temperature CME question mark.
So you want me to explain why it is negative magnetic resistance?
No. Sorry. The slide passed. So could you show some plots? Maybe the next
This one? Yes.
This one. Thank you. So yeah, I want to ask more about this statement toward the room temperature CME.
Okay. So here the statement is simply that the CME has been observed in materials at temperatures which reach maybe 150 in some materials. This is actually not even the best example. If I wanted to illustrate the highest temperature, I have a plot in some other material which shows the change in magnetic resistance of about 60% at 150 Kelvin. So what I wanted to say is that this, even though it's a phenomenon which is in many ways analogous to superconductivity, it can exist at much higher temperatures. So even in this DC transport, we observe it, let's say, at 150 Kelvin, and I do not exclude the possibility that someday we will discover some material in which we will see a strong CME at room temperature. And for optically induced currents, not for sort of this DC transport measurements, but for optical, we already observe it at room temperature. So, for example, this measurement was done at room temperature.
I see. So what about the insertion of this graph? Is this show there's no negative magnetic resistivity at 300 Kelvin?
Let's see. So this, I think they just, okay, honestly, I don't quite remember what the insert on this plot was. Yeah, you can easily check this. But I think they did not observe, I think that in this particular material, which is tantalum diarsenide, they did not observe CME at 300 Kelvin. So
observed, not observed. Okay.
Yeah, they did not observe it. Yeah, so I think it's they probably blew up this curve at 300 to show that there is no negative magnetic resistance.
I see. I see. Sorry, I have more questions. So
yes, please go ahead.
So I want to ask about so dynamical conductivity on your work. I showed your plots of chiral magnetic conductivity as a function of frequency. So could you show that? Yeah, maybe
this one. This
one is good. So yeah, your plot is the right one, right? So I want to ask, is there any analytic forms of this sigma chi over sigma 0 as a function of omega in the low frequency
Yes.
regime?
So yeah. So please have a look at this paper, which
Okay.
we wrote with Honk and Misha. So we have analytical formulas describing the frequency dependence using kinetic theory. So in particular, so I actually was puzzled by this for a very long time, because in linear response with Harman, we obtained this 1/3, and kinetic theory, once you know kinetic theory, right? So you just introduce this Berry phase, and there is this factor omega dot b, and this at finite frequency always gave this just 2/3, not 1/3. And so what we found here is that if you do it carefully, you find that apart from the Berry phase in kinetic theory, you also have to include magnetization current. And this magnetization current gives you exactly -1/3. And so you get +2/3 -1/3, and this gives you this 1/3. So of course, kinetic theory, I don't know how to sort of exactly match kinetic theory and this one loop computation, but at least at some small values of frequency, I think kinetic theory is adequate.
So is this 1/3 means the value of sigma chi at omega equals to 0?
Yeah. So for example, here this sigma chi is this e squared over 2 pi mu5, and here it goes to 1/3 of this value. But this 1/3 is really an artifact of weak coupling, one loop, or kinetic theory description, because if you do the computation, for instance, at strong coupling, then this sort of sharp unphysical drop is smeared out. And even with Harman, we already understood that once you include, for example, some finite relaxation time for fermions, then this kind of sharp drop is going to be smeared out by relaxation effect. And as Honk observed at strong coupling in holography, indeed, you get a much smoother response at strong coupling.
I see. How about the power of this frequency at the low frequency behavior? Do you know the power of this function?
You mean here, for instance?
Yeah. And your studies, yes.
Well, in our case, it doesn't make much sense to think about power, right? Because it's kind of very unphysical. Well, it's physical at leading order, right? But in the real world, I don't think it's a physical behavior. The physical behavior, it should be something like this. And I think it probably should be possible to fix this power, because it comes basically from relaxation. And yeah, I think on general grounds, probably you can figure out what the relevant, what the power should be, just assuming that it's due to relaxation.
Okay, thank you very
maybe
much.
I think we should.
Yeah. Sorry.
Sayantan has if you have a quick question, you can go ahead. Because you're probably done.
Hi, Dima. Just a quick question. So when you are studying this the Schwinger pair production problem and this equivalence between the entanglement entropy and the Gibbs entropy, so is it true for all electric field pulses, or there's some specific electric field dependence, time dependence, where you find this equivalence?
No, this is true for any electric pulse. So we studied specifically some, we considered a more detailed example of so-called Soter pulse, because there you can get analytical results. But this relation, I think, is general for any pulse.
Thanks. Yeah. And thanks for this exciting talk again.
Oh, thank you so much.
Thanks a lot, Professor Kharzeev, for this very nice talk.